Thank you for your introduction. I would like to thank everyone for giving me an opportunity to come here to talk about my research here today. Today I am going to talk about ultra-fast outflow in active galaxy nuclei of Seyfert 1 galaxy. My talk mainly is a literature review of recent results, and at the end I will talk about our recent observation with Chandra-Gratin spectrograph. Here I am working with Julia Lee and Mike Novak at MIT and Randall Smith at CfA, and also I work in collaboration with other researchers. Large-scale ejection have been detected in radio-low AGN, while radio-quiet AGN mostly show a small-scale radiative-driven winds. It is really Chandra and XMM made it possible to see this small-scale radiative-driven wind. And in Seyfert 1 galaxy, we have the view to these central regions. Here, the outline of my talk. I will talk a bit about what is the classification of AGN based on unified model, and I will talk about what is ionized X-ray absorber in AGN, and I will talk about two different types of ionized absorber in AGN. One of them warm absorber, another one ultra-fast outflow. And I will explain how we can constrain physical condition of ionized absorber using photoionization modeling. And also I will talk about possibility of unification warm absorber and ultra-fast outflow using a density, unique density profile. And also I will talk about, I will present our latest result of our group with recent Chandra-Gratin observation of PG1211. About nearly 15% of nearby AGN are classified as a radio load, while the rest are classified as a radio quiet AGN. This radio quiet AGN divided to two different groups. One of them are Seyfert 1 and another one Seyfert 2. In Seyfert 1, it is very bright in X-ray and ultraviolet observation, and while Seyfert 2 are very bright in infrared observations. This suggested that the Seyfert 1 and Seyfert 2, we are seeing them from different inclination respect to line of sight. And the Seyfert 2, we are seeing them from low inclination, while Seyfert 2, we are seeing them from high inclination. And the Seyfert 2, we don't have any view to central region, and central region are blocked by dusty torus around a supermassive black hole. And this unified model have been developed nearly 2 decades ago. In terms of what we learn from X-ray observation of AGN, we learn about thermal soft axis, which usually modeled by a black body, and we learn about non-thermal axis of X-ray observation, which related to corona above accretion disk, and this hard axis usually modeled by a power law. And we learned that there are some warm absorber and which could be related to outflow above accretion disk. And here you see this is a phenomenological model of X-ray observation. This is the black body which related to this region, and the power law related to this region. And warm absorber is this component which usually observed in soft band, and also we have warm absorber iron which we observe in around 7 kV. There are two types of ionized absorber. One of them historically called warm absorber because first we observed them in less than 2 kV. And historically it was only magnesium, silicon, and sulfur and oxygen which show this warm absorber, and later we see them in iron. And right now warm absorber phrase is used for those ionized absorber with velocity less than 10,000 kilometer per second. And the ultra-fast outflow are those warm absorbers with velocity much higher than 10,000 kilometer per second. And some of them reach the velocity of 0.1 to 0.4 speed of light. And warm absorber recently observed in nearly half of Seyfert 1 galaxy, while the ultra-fast outflow have been observed of 30% of radio quiet and radio low AGN. Here are the list of well-studied Seyfert galaxy. As you see, the ultra-fast outflow with a speed of 0.1 and up to 0.2 speed of light seen mostly in Seyfert 1 galaxy. And we also notice few of them has a redshift absorber. This blue shift absorber could be related to outflow toward us, while redshift absorber could be related to infall of matter to supermassive black hole. To study physical condition of a warm ionized absorber, we use a phenomenological model. The first two component, blackbody plus power law, model continuum of X-ray observation, while this component, photo emission and ionized absorber component, are used to describe the emission and absorption of ionized absorber. There are two different methods for fitting warm absorber and photoionization, one of them using X star dB, another one using X star to expect or X star to table. And these two methods are very computationally expensive and require a special technique. Recently, I worked on parallelization of MPI using MPI because previous tools was made with PVM, and recent supercomputer doesn't support PVM and mostly support MPI. And using MPI X star, we are able to run a parallel of X star for different free parameters. Usually the free parameters are column density and the ionization parameter. And we can make a grade of X star table model for different, a range of column density, for example, from 19 to 25, and ionization parameter from 0, logarithmic ionization parameter from 0 to 5, and we can use, for example, expect or ISIS to fit which column density and which ionization parameter are best to reduce the physical condition of ionized absorber. The fundamental parameter in photoionization modeling of ionized absorber are ionization parameter and column density. Ionization parameters are defined by this equation, where L is luminosity, ionized luminosity. Ionized luminosity in X star usually defined by luminosity integrate from 13.6 electron volt to 13.6 keV. And R is distance from ionizing source, and N is gas density. And column density defined by this equation, where delta R are thickness of ionized absorber. And using these two equations, we can constrain upper limit of ionized absorber, while lower limit can be obtained by this equation, where M is mass of supermassive black hole, and this velocity is maximum outflow velocity, which can be observed in AGN. Here we see the range of parameter for a sample around 42 radio quiet and 41 AGN from literature. From this paper, you see this is the result for ultra-fast outflow. As you see, the ionized absorber are in range from 2.5 to 5.5, and the column density are in range from 21 to 24. The red line describes the lower limit, and the black line here describes the upper limit of column density. And here you see the range of outflow velocity, where ultra-fast outflow have been detected. As you see, it is in range from 0.1 to 0.2 speed of light. Here you see the result of photoionization modeling of NGC 4051. In this paper, they model different warm absorber using 6 different absorber components. And here you see the plot of ionization parameter versus outflow velocity. As you see, there is a linear correlation between the ionization parameter and outflow velocity. When ionization parameter are low, the outflow velocity are very low, and where ionization parameter which is high, and usually it is on iron, the outflow velocity reaching 10,000 kilometers per second. And this linear correlation suggested this view of AGN. Here there is shock from accretion disk around supermassive black hole, and in this region, which mostly we observe in X-ray hard band, we see this very high ionization where the speed reaching 0.1 speed of light. While in this surrounding region, where the temperature is cooling and the speed of a gas is slowing, we see this component where ionization parameter also is lower. So this correlation suggested in this quasar we could have this schematic view of shock wind model. Another important parameter in ionized absorber is density profile of ionized absorber. Density profile of ionized absorber usually studied using a method called absorption measurement distribution, AMD. These methods are similar to emission measurement distribution. Absorption measurement distribution is defined as a distribution of column density with ionization parameter. Assuming a power law for density profile, using AMD, we can determine this index, power law index, and from here you see the result for 5 AGN, and using this correlation, the Behar obtained this index alpha is in range from 1 to 1.3. Recently, Tumbasi studied around 35 AGN, and he found that this index are in range roughly about 1.4. And here are blue are ultra-fast outflow, and red are warm absorber. So the warm absorber has usually a speed less than 10,000, and the ultra-fast outflow has a speed more than 10,000 kilometers per second. And this density profile suggested that ultra-fast outflow and warm absorber could be related to one phenomena in AGN. And for example, warm absorber from outer region and ultra-fast outflow from inner region. Here you see there is a correlation between ionization parameter and column density. At the bottom, you see there is a correlation between ionization parameter and outflow velocity and column density with outflow velocity. And Tumbasi, using this correlation, suggested that the warm absorber and ultra-fast outflow are related to a singular large-scale outflow with power law density profile, and they could be related to the same physical system. However, there is another study. In Tumbasi, they study around 35 Seyfert 1 galaxy. Here they study around 26 Seyfert 1 galaxy, and some sample is the same as Tumbasi sample. But here they use a spectral energy distribution for photoionization modeling, and they found that the correlation between ionization parameter and column density for ultra-fast outflow and warm absorber are not consistent with each other. They suggested that the warm absorber and ultra-fast outflow could not be related to the same systems. in these two papers, they use two different methods. Here they use power law, but here they constrain spectral energy distribution of ionizing source. Now I am talking about our recent result, which obtained with Chandra grating spectrograph. We observed PG1211, which previously observed with XMM Newton. Pound in this object have been observed several times with XMM Newton, and since 2003, pound have been detected outflow velocity with 0.08 speed of light. And this outflow velocity have been detected in several warm absorber of carbon, nitrogen, oxygen, neon, sulfur, and iron. And also there is some paper which they claim that there is infall with redshift between 0.2 and 0.4 speed of light. And recently, Pound claimed that there is two component outflow velocity, one of them 0.14, another one 0.07 speed of light. However, there is two other paper. They use one of them, one of XMM Newton, which already studied by Pound, and there is another paper recently which they use new star observation, and they contradict their result which found by Pound, and they claim there is no ultra-fast outflow. Our recent observation done by Chandra grating spectrograph, and we use 430 kilometer second exposure, and our observation done by 6 observation over 9 days. And as you see, most of our observation in low state, one of them, it is in high state, in bright state. And here there is a hardness ratio. We wanted to see if all observation, if there is any change in hardness ratio in all observation. As you see, and there is a very minimal variation in this observation. And in order for our study, in order to make our study very consistent, we excluded this 4 observation because it is in very bright state. And the warm absorber are very strong when it is in very low state. So we combined this 5 observation, and we did a time average study. In order to make our photonization modeling, we construct a spectral energy distribution. Our observation was simultaneously with radio observation and HSTC observation. We use our radio observation and HSTC observation and archival infrared and optical data together with our Chandra observation, and we made a spectral energy distribution. And using this spectral energy distribution, we made this component, warm absorber and photon emission, for fitting the time average Chandra grating observation. Here you see the spectrum of Chandra observation. The red line is a fitted model did it using a blind searching code. As you see, there are several component ionized absorber here. And we found that this component has velocity of 0.06 blue shifted. So this component could suggest that there is a ultra-fast outflow in PG1211. And here you see the iron emission from K-shell, from natural region far from the central region of AGN. One of the important issues in fitting ionization parameter is the thermal stability of the ionized absorber component. Thermal stability of ionized absorber can be studied using an effective theoretical tool called stability curve, in which the gas temperature plotted against the pressure. When the slope of this curve are positive, the gas in this region are stable, or they are in thermal equilibrium. This means cooling and heating are in balance. So in this thick blue region, the gas are unstable. So the absorber component could be exist only in this region, not in this region where are unstable. So for photoionization, we use this theoretical tools to constrain the warm absorber. Right now, the warm absorber, we fitted only one component warm absorber, which is here. If there is iron, it could be here. Because the iron only exists in this region, while other components can exist in this thing. This is a plot of ion fraction. We plotted, this is temperature, this is helium-like, hydrogen-like, neon, magnesium, silicon, and this is ionization parameter. And this ion fraction, as you see, the ion fraction, for example, for neon, magnesium, silicon only exists when they are stable, when they are in this region. But for iron, it is only in this region, which means that they have the ionization parameter more than 4. Here is a summary of my talk. Just to conclude, the warm absorber and the ultra-fast outflow are seen in Seyfert 1 galaxy. The warm absorber are those with velocity less than 10,000 km per second, while ultra-fast outflow are with velocity more than 10,000. To constrain the physical condition of ionized absorber, we use photoionization modeling, and the free parameter in photoionization modeling are ionization parameter and column density. And in order to make photoionization, we make a grade of photoionization models, and we fit this photoionization model and spectrum to find what is the best ionization parameter and column density. And using this method, we can determine what is the density profile of if there is any unification of ionized absorber, what is the density profile of this ionized absorber. And I also present the latest result of our Chandra grating observation, which suggested that there could be the ultra-fast outflow with 18,000 km per second, 0.06 speed of light, which is consistent with Pond recent paper. Thank you for your attention. I am happy to answer the question.
What sort of mechanical power is being carried in these ultra-fast outflows?
There are different theories. One of them is a magnetic hydrodynamic theory, which, as you see, there is a simulation using magnetic hydrodynamic theory, and as you see, it's reached the speed of 0.1 speed of light. Other theory could be frame Drake in relativistic theory, but this is not relativistic theory. This is magnetic hydrodynamic theory, and using magnetic hydrodynamic theory, in this paper they study quasar, and they found that it reached this speed, which is consistent with observation. So this jet could be powered by magnetic hydrodynamic energy of the accretion disk, or could be related to angular momentum energy of black hole.
But from your observations and model, can you estimate the number, the amount of power? This is the mechanism, which is
yes. For a fitting model, we can only find what is the best for the fitting photonization modeling, and unless the observation, we can only find what is the best ionization parameter and column density. So we couldn't find what is the energy which driven this jet. This is the work which should done with theoretical modeling. Yeah.
Questions. In your stability curve, was that for solar abundances?
This is, yes, for solar abundances.
Yes, so if you go to higher abundances, the wiggles get larger, and you get less stable regions.
Yeah.
And the abundances in quasars and AGN are typically a few times solar. So you'll find when you do it, that the wiggles are much bigger. And this is in another paper by Chakraborty et al.
Yeah, it's interesting. Point.
And the other one is when you do how you do the line identification. Is it you go through finding features and then identify them with a line?
And we use a Gaussian absorption model.
How do you find a line and give it it has an energy or a wavelength, and you say, okay, that's best matched to some particular line.
Yeah, we use a series of hydrogen-like and helium-like lines, and there is, for example, 4 lines each.
So the problem with this approach is that the resolution of the gratings that we have, you've got a lot of line blending. If you do a full model of a photoionized region, a large fraction of the lines are actually blends of more than one line. How do you deal with that?
Because we use the helium-like and hydrogen-like, it could be some line blended, but because the helium-like and hydrogen-like are very strong, as you see, this is the feature which is silicon, and this is the feature of magnesium, and it could introduce some uncertainty when there is blinding.
Is your density profile related to cloud distribution or just a smooth medium?
Pardon?
Is the density profile measured as clouds per unit volume or just density of the smooth medium?
This density profile, yes. You are talking about this density profile.
Yeah.
This density for the number density, but the column density is the density which is unit centimeter to -2. But this number density has centimeter to -3, and from this AMD we can plot and find what is the distribution of this number density.